In this video, we use the skills that we previously learned involving quadratic functions, like finding the vertex, to analyze interesting questions about projectile motion and maximizing cost and revenue. Let's get started. So to begin, I want to talk about a couple of ways that we remember from our previous video of how we could write out the equation of a quadratic function. Namely, in the middle here, we have f of x equals ax squared plus bx plus c. That was our general form to write out your quadratic model, degree 2 parabolic trajectory. So some examples today that we're going to be looking at that have this type of model involve perimeter and area, cost and revenue, and even projectile motion. So if you take a look at the picture on your screen, you'll see that we have a situation where something is being either thrown into the air or maybe launched into the air, such as a rocket, let's say. It leaves the building at a certain height, it travels to a maximum point, which would be called our vertex, as we studied in our previous video. And at that maximum, it would then have an axis of symmetry that cuts down the middle, and on both sides of that line, you'd be the same distance away at any point. Now, some questions that we're going to be answering today in this video are, when would my object that I throw into the air be at its maximum height, right? Using our vertex formula from last time, we'll be able to answer that question. What would the maximum height be? So both of those questions can be answered with your vertex formula. If you forgot, remember your vertex, which was the point h comma k, where h was the opposite of b over twice a. So if we have the equation already given to you of the quadratic model in this form ax squared plus bx plus c, we can simply put in b, put in a, and do arithmetic. We would have our h value, in other words, the when, our value would be at its highest location. And then to find the k value, if you were with us in our last video, hopefully you practiced quite a bit, you noticed that k was when we actually just plug in the answer that we had for h. So it's like f of h, or f of negative b over 2a. In other words, once you know the input, you put it into the function's equation and you get the output. And that would give you your maximum height in this case. So that's one of the questions we'll be handling today. How do I find the maximum and when it occurs? Using the vertex formula. The second question we'll be talking about is, in the case of projectile motion, when would your object hit the ground, right? So if something comes up, on planet Earth at least, it must come down. So when it hits the ground, we want to know when that would be, so either we can get out of the way or we're ready to receive whatever the object is. So that would mean we need to know when your value is on the x-axis, if the ground is represented as the x-axis in your model. So if you remember, when you hit the x-axis, that's called an X intercept. So to find X intercepts, that's when you're actually going to be using the situation where you let y equal 0 and either use factoring or the quadratic formula or complete the square. So we'll take a look at those situations in this video. Now the hardest thing for students, I will acknowledge, is getting the model right. If I give it to you, most of the time you can use the right formulas to answer the question. But how do you create the model just from a word problem? Well, you take it one piece at a time, you don't quit, and maybe draw a picture. So let's go ahead and get started with an easy one on our next slide. Example 1 says, Joe has 3,000 feet of fencing, and he's going to enclose a rectangular field. So the very first thing I recommend with any word problem is not to quit, right? But to draw a picture, if you can, to describe a situation. So if we know that it's a rectangular field, maybe we'll draw a picture of a rectangle. Now there's various ways that this rectangle could look, right? We know that a rectangle, this is a very badly drawn rectangle, but a rectangle is one in which we have 4 right angles. So if I had drawn it perfectly, you would see that they are meeting each corner at a 90-degree angle. So please forgive the bad drawing. The basic idea, though, is you draw the rectangle and then you see what have they given me. Well, they've told us that Joe is going to use 3,000 feet of fencing to enclose this rectangle. And the two types of measurements that we've studied in the past involving rectangles or any two-dimensional object is measuring around the object and then measuring to cover the surface of the object. One is called the perimeter, the other is called area. So if they've given me the amount to enclose, that would be the perimeter. So basically going around this rectangle, we're going to use up 3,000 feet of fencing. In other words, they've given me that the perimeter equals 3,000. That was given to us, 3,000 feet. But we also remember that if we were to call one side of this rectangle our length and one side our width, so L and W for length and width, let's say, that we could describe length and width now using this information. Now there's a couple ways to do this. One is very formulaic. If you think about perimeter, you would remember that to get the perimeter of a two-dimensional object, two-dimensional surface, you would simply add up the sides around, right? Peri meaning around, meter usually is the unit of measurement for length. So you're measuring around. Okay, well that would mean we'd have to measure length plus length, width plus width. In other words, the formula for a perimeter of a rectangle, 2 copies of the length plus your 2 copies of the width, right? Once you have that, what you could do, if you were being kind of clever, is you could say, well, notice how, if I set that equal to 3,000, they're all even, right? So I could divide everything by what number? 2. Good job. So that would mean that 3,000 divided by 2 is 1,500 equals my length plus my width. The reason I would recommend this approach, if you're very formulaic, it gives you a place to begin, right? You know that length plus width together must equal 1,500, since 2 copies of the length plus 2 copies of the width must add up to 3,000. In other words, now you could actually write length in terms of width. For example, you might decide to say that my length is going to equal, how did I choose it here? Yeah, that my length is going to equal just x, let's say, and that's because they've told me here in the next part that length is x. So you could say if length is x, let's get another color here, we'll use white. If length is x, then what we now know is that 1,500 is equal to x plus w. All right, so what does that mean if length is x? Now you could have let the width be x, but we just chose to obey the instructions here. Let's let length be x. Well, that means we know what w is in terms of x, don't we? Solving for w, we now know that w must be 1,500 minus x, right? So whatever our x is, we're going to subtract that from 1,500, and that is our width. So we can now say, okay, we now know that width is equal to 1,500 minus x. Now this should make sense, because if we were to add up all 4 sides, 1,500 plus x, oops, not sure why that happened, but 1,500 plus x minus x would actually wipe out the x's, and then 1,500 plus 1,500 would get us back to the 3,000. So let's go ahead and clean that up a little bit. Let's see if I can get that cleared off here. Oops. Let's see here. Clear current page. There we go. So if we were to actually add up all the sides, we would in fact have our 3,000. Okay, so where does that leave us? I know I erased it all, but I'll basically summarize where we are at this point. What we found is that the length was equal to x. What we found was that the width was equal to 1,500 minus x. What we are after in the very first question now is the area. So if we think back to that situation with our rectangle, area is coverage, right? So what we're trying to figure out is how can I best cover this rectangle now that I've interpreted length and width correctly. Now if you didn't like the way we went about finding the length and the width, the alternative would be to simply think it through without a formula. You could have simply said, well, I know that to go around I'm using 3,000 feet of fencing. That means that if I use x for length, I've really used 2 copies of x. So 3,000 minus 2x. And then since width is going to be cut in half, dividing 3,000 minus 2x, you'll get 1,500 minus x. So there's lots of ways to interpret the situation. If you don't like the first way, try the second way better. Okay, now that we have expressed length and width in terms of only one variable, we can express area. Area will depend only on x, which is our length in this case, as they've asked us for. But we also notice that area is equal to, for a rectangle, do you remember? Yep, that's right, length times width. Very good. So we want to first create the picture to describe the situation. We then want to figure out the quantities in terms of one variable only, so this time x, which was our length. And then finally, we're going to find the model that makes the most sense based on what they're asking. They're asking us for area, and area is equal to length times width. So let's plug in what we have then. The length we're calling x. The width we're calling 1,500 minus x. And you could definitely leave the equation like that, but if we were to actually go through the process of distributing, we could then see the equation in what we call descending order, which might be more beneficial. So go ahead and do the distributing and see what you get. Feel free to pause the video and do it yourself. All right, when you distributed that x, did you get 1,500x minus x squared? Yeah, that's what I got, which means that if you were to write it in descending order, you'd have negative x squared plus 1,500 x. Now, that might look familiar to you. Hopefully, it reminds you of our previous slide, right? We said that if we had a situation where our function or our y value, your output, was equal to ax squared plus bx plus c, that was the general form for our quadratic model, then the vertex of that equation would be found by finding the point hk, right? and HK would be the maximum or the minimum point. Okay, well in this situation, how is our parabola opening? If our leading coefficient is negative, it must be opening down. In fact, you're welcome to click on the Desmos link at any point as you're watching the video in your slides, the PDF or the PowerPoint slide, and it'll open up the actual parabolic trajectory for you. I might even show you that at the end of this presentation here. So what we know here is the parabola is in fact opening down. So the next question they're going to ask me for after creating the model is to use it to answer some questions. So let's see what the first question is. In B it says, for what value of x would your area be largest? Well, largest is maximized, right? So if we're talking about the area model being a parabola opening down, it would have a vertex, HK, that would be a maximum. So to find that answer, we would simply use the vertex formula, wouldn't we? So let's take a look at how we would do that in this case. We would say, well, our vertex would be found by first finding the x component, which is called h, and that was the opposite of b, so negative 1500 over twice a. So a here, be careful, what is a? It's negative 1. Good job. So we're going to take 2 copies of negative 1, and we're going to simply do some arithmetic here. Make sure you take your time with the arithmetic. If you make a mistake here, it will mess up your entire understanding of the problem. So we have negative 1500 divided by basically negative 2, which means you have a positive, 750. So what is this telling me? Well, in that ordered pair, your x input is 750, but what was x? So this location here has a vertex, we would say. The vertex has the ordered pair so far of 750 for your x value. Oops, that's kind of an ugly 5. 750 for our x value. And what is the y value? Well, that would be k, right? How do you find the output, the y value, if you know the input, the x value? You simply input your x value. So you would take a minute and you could plug in to find your k. You would need to plug in your 750 into the area model. So if you take a moment and do that, feel free to pause the video to do that. You're literally taking the opposite of 750 squared, and you're adding 1500 times 750. So feel free to take a moment and complete that arithmetic. An alternative way I've heard students tell me, they say, you know what, I don't want to plug it into the formula. If that's really x, I know that x is my length. So I could then plug in x to find my width, and then 1500 minus 750 is 750. Now I know the dimensions, right? It's a 750 by 750 rectangle. In other words, it's a square, okay? So what ends up happening is if you were to multiply your length times your width, your 750 times your 750, you should get the same result as if you had found the area by simply inputting 750. The result in the end should be a big number, 562,500. And that would now be feet times feet, so what would your units be? Yep, square feet. Which makes sense because area is going to always be in square units, right? Whereas linear units would have just been in feet. Okay, so that would be the k value that is in our ordered pair here. So to answer the question now that you've fully found the vertex, what is B asking you? For what value of x is the area largest? So they're asking you for an x value. What would your answer be here? That's right. It would have to be 750 feet. Yep. That is the answer for B, right? When we let our length be 750 feet, we can then expect for the area of our rectangle to be maximized. So if you are interested in using a fixed number of fencing to enclose the most space, maybe for your animals to graze in, right? Or for your kids to play in, this would be the proper dimension. These would be the proper dimensions. When the length is 750, and then correspondingly by plugging in 750 for width, it's also that the width is 750. So in other words, a square was actually your best bet. C asks a slightly different question. In C, it asks you to find the maximum area enclosed. Well, we've already done that, haven't we, by completely finding the vertex? The maximum area enclosed was 562,500 square feet. So that would be our maximum. We've actually talked about this in a previous video. When someone asks you to find for a parabola, for a quadratic model, when they ask you to find the maximum, that is the output, right? That is the y value. But when they ask you when or at what value do we have a maximum, that is the x value, or h of your vertex. All right, so if this was a little bit overwhelming, feel free to pause it, go back again, and watch it over and over again until you understand the basic setup of that type of problem. All right, again, feel free to also check out the Desmos graph provided. Okay, so let's head over to our next example. A little more complicated, so deep breaths, maybe take a drink, not a strong drink, of course, maybe coffee, might help you. Okay. It says a certain product has the following known relationship between its price and its demand, X. So price P, demand X. So let's take a pause before we get a little overwhelmed. And remember that we already understand how this works if we've ever bought anything in our lives, right? The higher a price of an item, probably the fewer items you want to purchase, right? When an item costs too much money, you usually don't want to buy it, or you don't have as much money to buy it, perhaps. So the price and the demand in a free market system affect one another, don't they? So here they've actually done the research. So let's suppose that we're talking about an item, maybe one of my fancy pens that I used to like to change colors, right? Maybe that pen has been market tested, and they've discovered that the most that someone is willing to pay is $20. Okay, if that was the case, then we could say that the price is always going to be fixed between $0 and $20. More than 0 because we're not giving the pen away, and at most $20. Okay, so P is between 0 and 20, as you can see here. Now what they found is that as we raise the price, there's a certain linear relationship between price and demand, X. So for example, you can see in the demand equation that they've provided for us, let's suppose that the price of the pen was $1. Well, it says that you could then multiply -5 times $1, because the price would be 1, which would be -5, and you could add 100 to it, which would be 95, which would mean if we price the pen at $1, we would expect for the demand for the pen, the number of pens we expect to sell, to be 95 pens, okay? But what if we price the pen at the full $20? Look what happens. 20 times -5 is -100, and now no one's buying our pen. So we know somewhere between 0 and 20 is the perfect price to increase the demand. So there is a point where you can overprice something and no one wants your product, right? So we have to pick this perfect price in order to maximize the demand, okay, which hopefully would maximize our revenue for the business owner. So let's take a look at the first question. In A, it says, can you write the company's revenue, the money coming in, the revenue model as a quadratic function of demand? X. So they want our function for revenue to only depend on demand. They've also given us another piece of information. This equation, R equals P times X, it seems like another piece of information that you have to memorize, right? It kind of is, to be honest. Kind of like the area of a rectangle is equal to length times width. We always have to have that in our mind. But this is one that you already realize. Let me tell you why. If I told you that the price of the pen was $5, and then I told you that I sold 10 of them, could you tell me how much money is in my cash register, assuming that I haven't paid any overhead or anything yet? Yeah, you would say, well, the price of the pen was 5, and I sold 10, so 5 times 10 is 50. And that's how much money should be in the cash register at that point, assuming there was no money prior. Well, that's exactly what this equation is saying, so it's something you already intuitively know. Revenue, assuming that we have no other investors, is always price times X, which means X is the demand, the amount that we expect to sell. Okay, so we keep that in mind as we build our revenue model. So let's take a look at how that we begin. Just like last time, area was length times width. This time, revenue is price P times demand X. Okay, so that's where we begin. Let's see how we could write this equation only in terms of demand. So we only want the function to depend on X. So we take a look here and we notice that we have P in the equation. And so the way we have to handle this cleverly is to say, wait a second, could I express P as a function of X, price in terms of demand? And I could if I go back to the original demand function that they gave me, right? So instead of X in terms of P, could we write P in terms of X? Yeah, go back to your previous algebra skills that you've learned in the past and solve the first demand equation for P. So take a moment, pause the video, and see if you remember how to solve for P. Get P by itself. Okay, let's see how you did. Hopefully you subtracted perhaps 100 on both sides, or maybe you moved 5P to both sides. I think that's what I'll do. So if I move 5P to the left, I would have 100, and then if I move X to the right, I'd have to subtract it, minus X. Then when I divided by 5 on both sides, I would end up getting that the price, P, in terms of X, would be 100 divided by 5, which is 20. I'm going to write that at the end, since that's my constant. And this is a -1x. If you divide -1 by 5, you can either write -1/5 or -0.2. Either way, that's fine. I'll keep the fraction for now, -1/5 x. Now what we've done is we've said the same thing, right? This is still how price and demand are related, but instead of x in terms of P is now in terms of X. Okay, so we've done a little bit of manipulation. We haven't changed anything so that we can come back here to our revenue model and say, revenue in terms of X only is the price -1/5x plus 20, and that 20 again came from 100 divided by 5, right, times X. Now, just like we had for our area model in the last example, we could leave the model like this, but it's more beneficial to us if we distribute and rewrite it in descending order. So again, feel free to pause the video and see if you agree with me about what this would look like. Did you get negative 1/5 x times x is negative 1/5 x squared? Good. And how about 20 times x? That's positive 20x. Good job. That would mean that our revenue model in terms only of demand, or in terms of x, is negative 1/5 x to the second power plus 20 copies of x. Okay, that is what type of function? Degree 2, so it's a parabola. Good job. A quadratic model. And since the leading coefficient is negative, how does this parabola open? Down, exactly. So if we were to look at Desmos, we could see it right now. Feel free to click on that link in your notes, or just continue working by hand. You would see that this parabola has a vertex HK, which is a maximum. Okay, so let's go ahead and continue answering some more questions, and we may need to find the vertex if we are asked about maximizing. Okay, so let's take a look at B. B says, well, what would the revenue be if 15, let's say, pens were sold, right? If 15 items were sold. Well, that would be demand or that would be price? That would be demand, right? So this is saying when X is 15. That's what that's saying. In other words, we're asked to find the revenue R at 15. Well, this is an older basic algebra skill, right? Can you plug in an input and get the output? Let's see if you can do it correctly. Again, feel free to pause the video and practice this. You would have negative 1/5 times 15 to the second power plus 20 copies of 15. Okay, so after following your order of operations, squaring your 15, multiplying it by negative 1/5, multiplying 20 and 15, and adding everything together, you should be getting the revenue of $255. Well done. So if we sell 15 pens, we take in $255. Now, revenue is not the same as profit. We probably have overhead to pay, people that we've hired, the rent, etc., for where our establishment is. But at this point, that would be the revenue. Okay. So let's go ahead and go a step beyond that. Now we know that at any certain demand, we can anticipate what the revenue would be. But as a business, you don't want to just hope to achieve a certain amount of revenue. You want to have a game plan. And that's what problem C is all about. It's forward thinking, okay? So it says in problem C, what demand would maximize my revenue? Okay, so this is the forward thinking question, right? What demand would maximize my revenue? Well, maximize or minimize, depending on how your parabola is shaped, is all about the vertex. That's right. So we're going to say we need the vertex. And again, our vertex formula from our previous video could also be used, could also be solved here by completing the square, but this was the faster method we said. H would equal the opposite of B. So in this case, remember A, B, C. B is 20, so the opposite of 20, over twice A, right? So 2 copies of A, where A was negative 1/5. Again, take a moment and work out the arithmetic here. You can use your calculator if you need to. Remember, you could also use the decimal. What I will tell you, if you're putting it into a graphing calculator in one step, you would need to put parentheses around your entire denominator so that the calculator understands that that all belongs in the denominator. Okay. So after completing the arithmetic there, you should be getting that we would have a demand of 50 that would be necessary here. We would need to sell 50 items. Okay, so what we've just found is the input for this vertex, right? That's an X value. X was demand. So we would need a demand of 50 items. Notice the second part of the question, though. What is the maximum revenue? So what are they asking for that part? Yep, that's right. They are asking you for the Y value, the output, right? The K, if you will. And to find the K there, we would need to input 50. So we would say, to find my K, I would say, I need to take my revenue model and say, what is the revenue when I have a demand of 50 items, when I can sell 50 items? So again, just like in example B, in example part B here, we're going to input 50 into our model, negative 1/5 of 50 squared plus 20 copies of 50, and we're going to see what we get. Again, feel free to pause the video to do your arithmetic and check if you get the same result as I got. Did you get $500? Yeah? So what we're saying is that we can expect to get the most revenue coming into our business when we sell 50 items. What will that amount of money be? 500. So that would mean that if you have overhead of 300, your profit would be only 200, right? But at least we'd maximize the amount of money coming in as a business, which we need to do to cover our expenses and to hopefully make a living. Okay, so now we know what to aim for. That's the importance of using algebra in this sense in order to find the target, right? We want to shoot for 50 items being sold. Now, how are we going to do that? Well, we could do all kinds of things, right? We could lower the price. We could do an advertising campaign. But since we already know how the price and the demand are related, a good thing to do might be to say, here's the demand I need. Let me figure out the price that would most likely bring in that clientele, okay? So let's go ahead and take a look at the last question, which asks us something of that nature. The last question says, okay, to maximize the revenue, which is our goal, right? As a business, this is the goal. To maximize our revenue, for what price should the company sell the product? So should it be $1? Should it be $20? Should it be $10, $5, $8, $12? What should it be? We don't want to guess. We want to know going into our business projections here. Okay, so what we'd want to do is say, okay, well, originally we were given the relationship between the demand and the price. Now, you might be wondering, what if I open a business? How am I going to know the relationship between the two? Well, you can look at market analysis. You can look at previous companies who have sold pens or similar items, and you can see what the most someone was willing to pay, what the least they were willing to pay, and then you could actually run some type of regression analysis. And you're welcome to contact me about that if you have more questions that you're curious about to find that relationship, okay? So since they provided it for us, what we would want to say here is that the price depends on X, and it was -1/5. It depends on your X, and then we would add 20 to it. But we just found what X was, right? The input that we are going for, the demand that we were going for, was 50. So take a moment and do the arithmetic there. If we know that we want the demand to be 50, what should the price be? You can see it kind of here, right? -10 plus 20. Yeah, it's $10. So we should be selling each item for $10. So if we sell each item for $10, we can expect to maximize our demand for 50 items, which would then maximize our revenue for $500 coming in. Okay, so that was a little bit convoluted, I'm sure it felt, but with more practice, you'll get the hang of this, right? The ultimate goal, maximizing, uses Vertex, right? But you had to first build your model to recognize that that's even what we're doing. Okay, we have one more question. This time they give you the model, so deep breath. It's not as hard. Let's get started with example 3. It says a bullet was fired into the air at a 45-degree angle to the horizon or the horizontal. They then give us some more information. You might not care about it. It says the muzzle velocity of the gun was 100 feet per second, so this is a very, very low muzzle velocity. Okay. The height of the bullet is modeled below by a function of the horizontal distance x from the firing point. Okay, so if none of that makes any sense to you, let's go ahead and take a look at the model at the very least and see if we can at least get an idea of what type of model this is. Okay, h of x, so the height of the bullet, depends on x, where x was a horizontal distance. So let's go ahead and take a look at, on a graph, for example, what this might look like. So we're told that the model is -32 over 100 and the denominator squared. That's your coefficient of x squared plus x. Now, what bothers a lot of students here is the fraction, right? So if you are someone who is bothered by this, keep in mind that instead of writing a as -32 over 100 squared, you could also notice that's the same thing as -32 over 100 times 100, or in other words, let me write it here, see if I can do it so you can see it. That's the same thing as -32 over 10,000. So if you wanted to write it as a decimal, that's the same thing, right, as simply saying -0.0032, right? So if we recognize that we have the option to write it as a decimal, I think that can alleviate some of the anxiety for most of my American students, at least, because fractions tend to cause anxiety amongst most American students of mine. All right, so that's your leading coefficient. That's your A, -0.0032. You might be wondering, Professor, why would they give it to me as a fraction? Do they want to kill me? No, that's not what they're trying to do. What they're trying to do is actually show you, if you have some intuition about what this equation is saying, they're showing you where this equation came from. It wasn't magically discovered, right? The equation here is actually coming from the fact that what goes up on planet Earth, so if you launch something from the ground, let me get my color here, black. If you launch it from the ground, let's call that the origin. And it goes up and reaches a maximum at the vertex and then comes back down, if that's its trajectory, and hits the ground. Something like this is happening. What's interesting about on planet Earth, right, is we have gravity, and it turns out that gravity is a known constant. It's a force that pulls objects down toward the ground, right? And the actual unit of measurement for gravity's acceleration toward the ground is actually negative, because it's pulling you down, 32 feet per second squared. That's where the negative 32 comes from. Now you might be wondering, if you're curious at all about this, where is the 100 squared coming from? Well, that has to do with the muzzle velocity, right? So they're working against each other. The bullet is being fired at a 45-degree angle, so it's actually more like this. I apologize for the improper drawing. So at a 45-degree angle, something like this is happening. And so what's happening is it is reaching, in fact, its maximum at its vertex. But what we notice here is that because you're firing up, right, that 100 feet per second initially, the muzzle velocity, is counteracted by the force of gravity. So they're fighting each other, which is why 32 is in the numerator and 100 is the denominator. The square has to do with the units because acceleration is in feet per second squared, and that's why we're having the squared units here. Okay, so if you didn't care about that at all, you could have fast forwarded the video. Hopefully, I should have probably told you first, but hopefully you're still with me. All right, at this point we had that A equals, as a decimal, negative 0.0032. Can you tell me what B equals? B is the coefficient of X, that's right. So B is 1. Okay, so if we have A and we have B, do we also have C here, just if you're curious about A, B, and C? Yeah, C is actually 0. Again, if you are curious about where this formula came from, because C is 0, that's telling us that we're launching from the ground. If C was 1,000, that would mean we're launching 1,000 feet above the ground. So all the components have a certain meaning here. Okay, so now that we kind of went through the equation, again, you didn't have to know where it came from if you weren't interested in it, but if you are going on to physics or calculus, you will need to start thinking about where these equations come from. Okay, let's take a look at what the first question is. In A, it says, how far from the firing point will the bullet be when it reaches its maximum height? Okay, so we hear the words maximum. That tells me what again? That's right, vertex. If I think maximum for a parabolic trajectory, or minimum for that matter, depending on how it's opening, right? That means vertex. Okay, so the vertex again is the point HK, where H is found by taking the opposite of B over 2A. So feel free to pause the video. We've done 2 of these now. I'm sure you can answer this question on your own. I have confidence in you, and come back and see how you did. All right, so when you did negative B over 2A, did you get the opposite of B was the opposite of 1 over twice A, where A was, as a decimal, negative 0.0032. And when you plugged that in, you would have ended up getting your H value of 78.125, right, as a decimal. So what is that saying? At your vertex here, remember it was actually the smaller one, at your vertex here, when I am 78.125 feet horizontally away from the starting point, so that's this distance from here to here, that is when my bullet should be at its maximum location. And that could have all kinds of meaning if you're talking about an indoor firing range and you want to make sure you have a certain clearance. You would want to make sure that your ceiling is maybe at least 80 feet tall, right? So that's when it's going to be at its highest location. Okay, the second question asks you in B, find the bullet's maximum height. Okay, so actually I think I just incorrectly spoke. That 78.125 feet is when it happens. Now what is the actual height? I made a common error, so hopefully you were tracking with me and saw that. So 78.25 feet is when it happens, but what is the maximum height? So the maximum height is your K value, right? It's your output. So to find that K value, what do? We input H, don't we, into our model. So if we use the decimal version, this would be H of 78.125, or in other words, the A value as a decimal was negative 0.0032 times our X squared, where X here is 78.125 squared, plus the X value again, 78.125. So maybe you've already set it up that way. If so, great job. Go ahead and do the order operations, the arithmetic here, and come back and see if you agree on the maximum height so we can know what that ceiling clearance should actually be. Okay, what did you get? All right. So this, I see where my mistake is. Wow, your professor's made 2 mistakes today. The arithmetic here that I looked at too quickly for my own good, that's why you're probably wondering, what's my professor doing to me? This one here was actually 156. Sorry about this. This happens sometimes when we're tired. So I'm showing you what not to do. 156.25 was the arithmetic you got there. When you plugged that number in here and here, what is the correct answer that you're getting? Well, yes, it's the 78.125 that I mentioned too quickly for my own good. Okay, so I was correct in a sense, but I was also very incorrect as to why. So I was correct that the elevation should be at least 80 feet, right? The elevation in the room should be at least 80 feet, but I was wrong because I put it in the wrong spot. So understanding why I made that mistake is critical. The arithmetic gave you 156.25. You input that number into your model. You square it, you multiply it by negative 0.0032, which was A. You add that number again, and the correct answer that you should be getting is 78.125. That's your correct elevation at the distance 156.25 feet from the firing point. Okay, now, apologize for the mistakes. Can we answer our third question here? How far from the firing point will the bullet hit the ground? Now, this question requires a little more thinking because everything we've done in this video so far has involved pretty much maximizing or minimizing quantities. Here, they're not asking you for that, though. What are they asking? When will you hit the ground? Now, there's two ways to answer this question. One is a shortcut, and one will always work. Okay, the shortcut only works in this case. Let me show you why. If you're thinking X intercept, you are correct. So when you're hitting the ground, that is what we call an X intercept, since the ground was on the X axis, the horizon. So to find X intercepts, what do we normally do? That's right, we normally let Y equal 0. Okay, so if we were to let Y equal 0, notice what would happen here. You would have 0 as your output equaling negative 0.0032 x squared plus x. Now, how would you normally go about solving a quadratic equation that's set equal to 0? That's right, factoring, completing the square, or quadratic formula. In this case, you technically could factor out an x, right? And you could get x times negative 0.0032 x plus 1, and then set each factor equal to 0. Or you could use the quadratic formula, where a is negative 0.0032, b is 1, and c is 0. Takes a long time, but you can do it, okay? But after all of that work, whether you do quadratic formula, whether you do factoring, you should get two answers, okay? One answer would be the x-intercept that we're interested in, right? The other one would be the initial starting point of 0, right? So you're going to end up getting two answers, either x equals 0 or x equals 312.5 feet. Now, that 312.5 feet would be our answer that we're looking for, right, after quadratic formula or factoring. But that kind of sounds familiar, right? Because in the first question A, after correctly doing it, we found that 156.25 feet was where we would be at the maximum, right? That's when the maximum occurs. But because of symmetry, since we launched from the ground, couldn't we have just doubled that to get our landing point? Yeah, so in fact, if you had just multiplied that by 2, you'd also get the same result. So if you're wondering, Professor, can I always do that? Can I always save time? Yes, if. If what? If you launched from the ground, right? And how do you know you launched from the ground? Because C was 0, okay? So if it wasn't from the ground, you're going to have to use quadratic formula here or factoring. Think about why that would be. If you had launched from up here, let's say, when you get to that location on the other side, that's not hitting the ground, so that's not symmetrical. You'd have to wait a little bit longer. So that's why the x-intercepts would have to be found a different way. All right, so we've done a lot in this video. I hope you go back and watch it. Try it yourself because, of course, math is not a spectator sport, and I'll see you next time.